Okay, so we talked about interference. There's lots of cases where it shows up in your life. Well, not lots, but there are some. But you can actually use interference to create very sensitive measurement devices. And so let's look back at that double slit experiment. And in the double slit experiment, if we remember, we had B times sine of theta was equal to m plus 1/2 lambda. And this told us where our zeros were, right? Alternatively, you could put in just m here, and that would be the maximums. So if we think of this in terms of a measurement device, if we know our width of or the spacing of our two slits, and we can measure theta, then we can calculate lambda. We can calculate the wavelength of the light we're looking at. But if you remember back from our temporal coherence work, it was difficult when we had multiple wavelengths and they would overlap a lot, because then we couldn't see the peaks very well, and we also couldn't see the zeros very well. So one thing we can do is we can add multiple slits like this. Just pretend those go on and on and on. And then what we find out is that the difference in length is delta L is equal to W sine theta plus n minus 1 times T, where T is this is T, that's the thickness of the material. Where n is the number of slits that we have. And this has to be equal for our maximums to m times lambda. So what's interesting is we do a lot of these n's, then we can start to get really good measurements of lambda, right? So interference fringes, this is just a note, right? Interference fringes for interferometers depend on lambda, n, and t, and it allows us to measure all three, though not at once. When we're measuring the location of these light or dark fringes, it can be difficult if they're broad, right? When we're, like I said, when we were looking at temporal coherence, when we had like wide peaks that were overlapping, they were very hard to tell apart. You just got a mush, right? So what's neat is the width of our fringes, as we increase the number of slits, is proportional to 1 over n. So where it's proportional to 1 over n. So as we increase n, we can increase the resolution with which we can see multiple wavelengths. So here, below here, is an example of a diffraction grating with 10 slits and one with 30. And you can see how increasing the number of slits by a factor of 3 has dramatically decreased the width of our peaks, right? So you can imagine if I have two wavelengths that are really close together here. So let's try to draw one. I'll tear the drawing. These overlap, right? Over here with our 10 slits. But if we have the same spacing, but with much narrower peaks, we can actually tell the difference between the two. We can actually resolve those two. So we want to use high numbers of these diffraction gratings, but unfortunately we lose a lot of light. And one of the real difficulties is as you add increasingly large numbers of these slits here, as we go down and go up, you have to maintain spatial coherence over the entire grating, right? And that becomes difficult. These can become quite large, and it means you have to use really coherent light. And if you have to use really coherent light and you don't start with a laser, you have to do filtering, and that loses a lot of light. So one solution to this is the Fabry-Perot interferometer. We'll say we have a diffuse light source. And all that says is that at every point, light goes in every direction. Okay, and if we take one single possible path here, by the way, this light source is located its focal length from a lens. In between this lens is a piece of glass that has like it's called partially silvered, but it's like a two-way mirror, right? Or a one-way mirror, actually is what I should say, where some of the light gets through and some of it gets reflected. And so what happens is the photon leaves, let's do it in green this time, photon leaves the light source, gets focused by the lens. Part has a chance of getting reflected back, but also a chance of going through. And then each time it hits one of these interferences, it has a chance of getting through and also coming back. And so we can ignore the ones that the possible paths that leave in this direction because they're lost to us. But the paths that go to the right will all be leaving at a certain angle, right? And roughly and parallel to each other. So all these possible paths of this single photon are all traveling parallel to each other. They go through this lens and they're all focused to a single point. Based on this angle, these paths will interfere or destructively, or sorry, will interfere either constructively or destructively. And so what you end up getting is for a specific wavelength, you get very, very clean fringes, and these are circular fringes, so they go around in a circle, right? That are based on the angle away from the center, right? So that's what this theta is. And so even a small change in wavelength, this is 589.0 nanometers, and this is 589.6. We're talking about 0.6 nanometer difference in wavelength. We get a dramatic change in the appearance of our interference fringes. This is a lot more efficient than the diffraction grating in terms of light efficiency. And these are used all over the place to very accurately separate out different wavelengths and measure them. Fabry Perot interferometers, very good for measuring the wavelengths of light. A classic interferometer is called the Michaelson Infernometer. Michaelson was just a genius at producing experimental setups. So we have a light source, and all the interferometers we talk about now are going to behave similarly in that we're going to take a silvered mirror, we'll call the beam splitter. Basically, it's a terrible mirror because when the photon comes in, photons coming in, hits this mirror, it has a 50% chance of going through and a 50% chance of being reflected. So if it's reflected, it goes up to this mirror, gets reflected back down, and then again, I'll show our camera on screen, has a 50% chance of being reflected, which is bad, but a 50% chance of going through, which is great. If it goes through, let's call the going through purple. So if it goes through, it goes through here, reflects off this mirror, comes back, has a 50% chance of being reflected down and coming through here. So what ends up happening, right, is that our photons end up traversing both of these paths at the same time. So as long as they're not strongly interacting with the object that you put inside of your test chamber here, the photon will be simultaneously reflected up on the red path and pass through on the purple path. And then they will come together and rejoin. Half the time they will go down and half the time they will continue straight. So you won't get a photon count for every single one that leaves your light source, but the ones that do come down, the photons will, the two phantom photons, right? The top path version of the photon and the straight through version of the photon will interfere with themselves and produce interference fringes that look like this. And the reason they're circular, again, is that if you were to look at this from the path of the light source, if you are deviating from this straight line a little bit, the path length changes will vary. So you get these circular fringes again. But yeah, so this works really well. You can actually measure really small distances. So small changes in this path length, or you can test different gases or things that don't absorb photons in here. When I was in, I don't know how my high school teacher did this, but in high school we had a Michaelson Interferometer that we could play with, and you could actually blow into this chamber here, and based on the pressure that you put in here, the index of refraction of light changes just a little bit. It increases, but that was enough that you could actually watch these fringes change. What happens is these dark paths just move in or out, right? You get and you can count how far they move or how many dark fringes go, and you can actually measure the changes in index of refraction as a function of pressure. Or if you were to move this mirror here, you could measure those small changes. And people have used this basic setup to do some pretty incredible stuff. The Michaelson-Morley experiment was an incredible experiment. You see the actual setup here. This was done in the basement of a building, and it had to be done at night because it was actually set up right next to a busy roadway. This was done in Cleveland, actually. But the basic idea of it is you have a light source coming in, a beam splitter, and then in order to make this measurement more sensitive, what they did is the split beam would bounce back and forth, back and forth, back and forth along each arm. So go back and forth, and then using this red, and back and forth, back and forth, and back and forth here before finally being recombined back at the same beam splitter B to possibly come down here that goes to a camera, or more realistically, someone's eye, because they were just sitting there watching it as this worked, because they couldn't take movies, right? This was obviously was a very old experiment. I think this happened in 1910 or something like that. And so what they did, what they used this for, was they tried to measure the existence of the ether. So they thought the Earth was moving, that light travel, because light is a wave. It's clearly a wave. They were like, well, waves always pass through something. Sound passes through air. Waves on the ocean travel on water, stuff like that. Then if light travels as a wave, it must be traveling through something. Let's call it the ether, and let's try to measure it. And so what Michaelson said was that, oh, look, we can measure this using an interferometer. If we rotate the interferometer and do a measure, and then as we move through the ether, because they also knew the Earth was traveling around the sun, as we move through the ether, there will be a Doppler effect, right? One of these arms will be compressed and the other arm will be unaffected. And so the apparent length of one of these arms will be smaller than the other one. And so as you rotate this around, so they took this large block of granite and they floated it in a bath of mercury. So this is a bath of mercury. It's a bath of mercury, and they would literally sit here, put their eye on this eyepiece, and then watch as they rotated this around very carefully to look for these changes in interference fringes. And the fact was that they didn't see it, which was devastating at the time. They were like, I don't understand why this is happening. I don't understand why we can't see these changes in interference fringes. The reality is there is no ether, right? But they didn't know that. Poor guys. There's a laser. We currently use this as in the Gravitational Wave Observatory. There are actually 2 or 3 of these spaced around the world. And the way that they work, and by the way, I think, was it a year ago or 5 years ago? I don't know. The pandemic has warped my sense of time. But it's basically a Michaelson interferometer. We have a laser beam that comes in. It gets split. Part of our beam goes up, and then we have a silvered mirror and a regular mirror. And so what happens is, it's not each time the beam comes back down, it has a chance of being reflected back up. And the ones that have a chance of being reflected back up over and over and over again come down. And eventually they come back down here. And again, they have a chance, 50-50 chance of coming through this mirror or going all the way down to our camera. The same is true of our purple beam, which comes through here. It can come back and forth, back and forth, back and forth. Some of the times it comes back through and then comes down here. And the end result is that even though this is 4 kilometers, these are very large interferometers, the effective length is 1,000 kilometers. So very long arms, which means you can measure very short, small changes in the length. And so what they were doing when they were measuring these gravitational waves is they were measuring, looking for these changes in these interference fringes on their camera as gravitational waves would shorten one of these arms relative to the other, just like with that ether measurement, right? With the ether measurement, they were hoping that there would be drag through the ether would apparently shorten one arm, which would cause a shift in their interference fringes. Well, gravity, it turns out, does that. So they were actually able to measure these gravity waves. It's pretty spectacular because it's a real confirmation of, well, we've had lots of confirmations of general relativity, but it's another one. I want to show you one more interferometer kind of like design and talk about the advantages of it. This is called a Mach-Zehnder interferometer, and one of the advantages of it is that imaging is possible. It's very sensitive to temporal coherence, but if you use monochromatic light, it's relatively robust. But if you use white light, both of these path lengths have to be very similar to each other. But this test, you can put something in a test cell, and then in the other cell, which is the same thing but without the object, when photons come through, they have a 50-50 chance of getting, oh, I used the wrong, green comes through here, 50-50 chance of being split. So we have purple goes straight, red goes up, red goes through the object, gets bounced, it has a 50% chance of coming up and a 50% chance of going this way, and the purple comes up through here through the normal cell and also has a 50% chance of going through. But the important part is that each time it goes through a beam splitter, you get a phase shift when it reflects. And that phase shift means that the top gets, whenever the top has positive interference, the side will get negative, destructive interference. So you can see that you have light in the middle here and dark in the middle here. So basically these are the inverses of each other. And so what ends up happening, right, is if a photons will go through both arms, and if the photon goes to the top screen, it will end up destructively interfering, then it will be constructed on the other screen. So you can actually do some really sensitive interference measurements, which are really cool. And this is basically fundamentally how an interferometer, the most pure form of an interferometer, if you ask me. And the last thing we'll talk about is a really interesting use of this, the Mach-Zehnder interferometer, which is a way to detect if a bomb is working or not. And this is a really cool example of how quantum mechanics is just crazy and how light can behave in really crazy ways. So let's say you're trying to determine if a bomb is a dud or not. And really the only way to do that is to explode it, right? Try to explode. If it doesn't explode, it's a dud. If it does explode, well, it's no longer a dud, but it's also no longer a bomb. So what we would love is if we could have a way of determining if a bomb is a dud or not without actually ending up with the bomb exploding. And it turns out we can do that with where we can save about 25% of the bombs, I think. I can't remember the exact percentage, but you can save a fraction of the bombs. So we have an interferometer here where we have a light source. The beam gets split. I'm going to use green now for one of the splits just because they use red for their beam. But one of the paths the photon can take is the top path. It comes through here. And one of the paths is the bottom path where it has a chance of interacting with the bomb. And now this is different than the experiments up here. And here, the photon does not interact with the objects. It is slowed down, but it's not absorbed, right? Here, the photon on the bottom path will be absorbed by a working bomb. Okay, so if the bomb is working, we're going to assume that it will set off the bomb. So we put a little photodetector on it, and if it sees the light, it explodes. And so we no longer have a pure interferometer, right? Remember how when we try to detect which slit the electrons went through the double slit experiment, it stopped being a double slit and you lost that beautiful interference pattern? Well, the same thing's going to happen here. So let's look at the first case. The easy case is if the bomb is a dud. So if the bomb is a dud, the photons will never interact with the bottom path. So it's almost like there's no detector, right? And the photons travel through both paths, and it's set up so that if a photon travels through both paths, it will constructively interfere at C and destructively interfere at D. So we get a flash at C. Now, if we have a live bomb, we have a couple options. The first is that no photon is detected. So the photon travels down, it turns out, remember, because if we have a live bomb, this is no longer an interferometer. So it's not going to behave the same way. So the photon's not going to travel both paths, it will travel one path. So the photon, if travels the bottom path, it hits the bomb is live, the bomb explodes, and we have a bad day. So that's one option. Another option is that the photon passes the top path, and then it gets to this beam splitter here. And remember, these beam splitters means it has a 50-50 chance of going either way, top to the top or to the right. So if it goes to the top, we get a flash, and we can't tell the difference between that flash and the flash we got if the bomb was a dud, right? However, if the photon travels through the beam splitter and we get a flash at D, we know that the bomb is live. It's an unambiguous example. So we stop the test. If we get a flash at D, we stop the test because the photon went to the top path and then split here. And that can only happen if the bomb is live, because it can only happen if the bomb could possibly sense the photon and react to it. So we stop the test, we take the bomb out, it didn't explode, and we can reuse it, right? So 25% of the time, so we have a 50% chance of the photon going top or bottom here, and a 50% chance of going top or bottom here. So we have a 25% chance of catching a live bomb without exploding it the first time. Now, if the photon went to the top path, which is and then went to C, which is a 25% chance, we couldn't tell the difference, right? So we'd have to run the test again, which means we have a 50% chance of exploding our bomb, but a 50% chance of not. And so basically we can run the exam until we're confident enough that it's a dud, or we run it until we get a flash at D, which means that our bomb is live but hasn't exploded. And the real average, because you're going to explode some, you're going to not explode others, is somewhere, I think, in the 30s. So you can get like 36% or something like that of your bombs without exploding them, which is pretty amazing that quantum mechanics allows you to tell if the bomb was capable of exploding without exploding it. I'm not sure if any people have set up this experiment, by the way, not with bombs, but with molecular tags, right? So you're not exploding, but you have a molecule that switches state when it senses a photon. And they've shown that this is true. This works. If you have a molecule here that can sense the path of a photon, this stops being an interferometer, then you get this result where 25% of the time you can tell if there's a molecule that could sense the path of the photon without actually activating the molecule. It's pretty cool.